In the last video, we came up with a general formula for looking at the runtime of some recursive function. And we came up with this T of n, which stands for the runtime of our recursive function. T of n is the runtime for f on an input of size n. And we came up with this formula, which was equivalent to this formula, d plus r plus c. So what I want to do in this video is apply that directly to our f of n over here. And so what would this general form look like for factorial? So let's look at that. Runtime for factorial. And so let's write out our general form first. D of n equals, or T of n, excuse me, equals d plus r plus c. So what's the time to divide in this case? Well, we've already labeled it with this step 1 here. Right, the step 1 tells us that the time to make our input smaller is just the time to do the subtraction right here and assign that to m, which is a constant operation. So it's O of 1. Let's skip the recurse for now. What about step 3? Step 3 is the time to arrive at the solution to the original problem. So that involves this labeled 3 line right here, which is just 1 multiplication, and again assigning that to a variable, which is also constant. So what might be a little more confusing is the step 2 right here. What is the time that it takes to solve the same problem on the smaller input? And if you think about it a bit, what we're going to do is exactly what we did with this recursive method here. Right? We defined a method. We defined a method f that calls itself. And so what we're going to do in this runtime analysis is we're going to write a formula or a mathematical function in terms of itself. Right, we're going to say that the time to solve the problem, big T, on an input of size n is the same as these two guys plus the time that it takes to solve the problem on an input of size n minus 1. That might take a minute to wrap your head around, but essentially what it's saying is exactly what this method is saying. Right? We defined a method that calls itself. Well, then the runtime, if we define the runtime for f as big T, then the runtime to call itself is also big T, just on a different input. And so if we simplify this a bit, O of 1 plus O of 1 yields O of 1. So it'll look something like that. So one thing you might say is, well, these lines over here only get run if n doesn't equal 1. Right? If this line fails, then we execute these lines. And you'd be right, which is why we need to impose this further constraint here, which is that this is only true if n is greater than 1. Right? And what happens if n equals 1? If n equals 1, only this line gets run. The runtime is different. Right? If n equals 1, then our runtime is just O of 1. Right? It's just a constant operation. T of n equals O of 1 if n is greater than 1. So if we make this a bit more compact, what we're going to say is T of n is equal to T of n minus 1 plus O1 if n is greater than 1, and T of n equals O of 1 if n equals 1. I noticed this mistake right here. There should be an equals. So this is the general formula for our runtime big T of n, and this is what we call a recurrence relation. And what we'll do in the next video or two is figure out how to solve this.